So this is this is how we are impressed with the first order methods. Now, what normally people expect while solving the large scale problem uh, with a first order method. So the method must be efficient enough to attack the non-linear, non-convex, and NP-hard optimization problems. Remember this. Our problem is a non-convex. Our problem is NP-hard. And our problem is non-linear as well. It's x1 square plus x2 square plus quadratic. So it may be quadratic or it may go even higher degree. So it is non-linear. So what we expect from the first order method to do that the first order method must be efficient enough to attack the non-linear, non-convex, and NP-hard optimization problems. The time complexity, redundancy, high memory requirements issues must be addressed efficiently by the method. The first order method must be generalized easily with respect to different scenarios that deals with large scale problems. Yeah, the method must be, we must be able to generalize it for all type of problems. It must perform well on convergence test. Yes, the convergence of the method is very important. So it must converge to its optimal value every time. So, and performance profile test also needed when applied on some strong numerical experiments. So now with this, we have set some background knowledge, means what is first order method and why they were so much important or so much in demand. So there are plenty of first order methods available. So we will discuss one method and see it that how it performs with respect to all other methods available. May not be so many, maybe one method available. So here comes the first order method, ADMM, alternative direction method of multiplier. So ADMM, actually, the ADMM algorithm solves the problem of this form. Remember, problems of this form it solves. So that means minimize f of x plus g of z subject to ax plus bz equal to c. So it has an objective and it has a constraint. But our problem was not having an objective or constraint. So our problem, again, I'll bring it here. Our problem was x transpose ax plus q transpose x plus c. So we need to minimize this. So it is an unconstrained problem. So we can always reduce it to this form. So we need to reduce it to this form. So there is a method which is available to make constrained problems to unconstrained. So here is, that is called Lagrange multiplier method. And it also comes with its variant called augmented Lagrangian method. So with the help of that method, I can construct a Lagrangian function. I can construct a Lagrangian function which looks like this. So if the problem is of this type, then we can always construct a Lagrangian function like this. And then this function we try to minimize. So now this is an unconstrained problem. Okay, so what actually ADMM is, I have not shown you. I have shown you only what ADMM solves. So ADMM solves this type of problems. So I need to apply the alternative direction method of multipliers. I need to bring my problem into this form, and then only I can apply. So now the next thing is how the ADMM iteration goes. So the ADMM iteration goes like this. So it updates variable by variable, means all the variables are not updated simultaneously. You see, first x is updated, augmin, L, the Lagrangian function, means if this is in the last slide, if this is our function to be solved, if this is the problem to be solved, then we will reduce it to Lagrangian function. Then we will apply ADMM iterations. So this is argmin L rho. Rho is the Lagrangian multiplier. X, Z, K, Y. So here X is the variable, Z is the variable, and Y is a dual variable. So Z equal to argmin Z, L rho X. When I write XK means kth iteration. Okay, I should write X value at kth iteration. Xk means the X value at kth iteration. Similarly, Zk is Z value at kth iteration. So that, remember, it is not power. So now, so these are how the iterations were. So there are two minimization steps and two variables were separately minimized. Now, the last one is called dual variable update. This one is called the dual variable update. Dual variable update. Now, the next thing is that this is another form of ADMM iterations. So you can bring it to the scaled form, it is called. So this is what the scaling we have done. So u equal to 1 over rho into y. So this makes the steps easy. So you can see this is called the same ADMM iteration, but another form, scaled form it is called. So here you see it is f of x plus rho over 2 ax plus bzk minus c plus uk norm, Euclidean norm square. And here also you see this and then this. There is some convergence conditions. There is some convergence condition for ADMM algorithm. So like residual convergence. So the residual convergence means this value should tends rk, r at kth iteration should be 0, means tending to 0, approximately to 0, where r is defined like this. Now, this is called primal residual, and sk must tend to 0, where s stands for the dual residual at kth iteration, sk. So sk is defined like this. So this is residual convergence. That means if rk tends to 0 and sk tends to 0 at kth iteration, then we can say that so k is the enough iteration have been taken, and now you can stop and display your result, display your output, and that output will be a good one because it is showing that they are converging. Now the objective convergence means the objective function is converging. So at the same time, you see the objective function is f of x plus g of z. So at kth iteration, it will be f of xk plus g of zk, which will converge to p asterisk, the optimal value, when k tends to infinity. K is the, if after infinite iteration, means after plenty of iterations, it will converge to the optimal value. Now, dual variable convergence. The dual variable also should converge to a value y asterisk when k tends to infinity, where y asterisk is a dual optimal point. So these are the conditions of convergence of the ADMM algorithm here in scale form. Now, the next thing is optimality condition. That means like we have first order optimal. So ADMM is a first order method. So we need to have the first order optimality conditions. So this is the first order optimality condition. A x asterisk plus b z asterisk minus c. So it is a primal feasibility, and the other one is dual feasibility. You can see the feasibility condition. So these things were derived from the first order condition. That means if you grade of L rho x, y, z. So if you differentiate this function, then you will get these conditions. Like, for example, let us go to that function. So you see this here, what will be grade L? Suppose I am differentiating it with respect to So if I'm differentiating it with respect to x, suppose, so what will be the value? So the value will be grade f of x, then f of x, then g, it will not be there because g is a constant, and then you will have here a, y transpose a, you'll have y transpose a here, and then the last term, if you differentiate, you will have rho into b transpose, rho into a transpose, you will have rho into a transpose a x plus bz, bz minus c, bz minus c. And now if you see here, grade of f of x plus, I can take a transpose away outside and can write it is yk plus sorry, not yk, it is y. I can write y plus rho into ax plus bz minus c. Now this is what called yk plus 1. Means from here I can have grade of f of x and a transpose into y. So if you put all this k here, then this will be yk plus 1. So that is the condition you see here, the optimality condition written. So here yk, instead of yk, it is y asterisk, and here it is x asterisk. So similarly, we can derive even this. Now, if you do it for grade L rho with respect to y, if you do, then equal to 0, then you will get this. See here. So this dou can be replaced by this grade actually. So it is sub-differential operator. So it is people use different times this notations. Okay. Now, so these are the optimality conditions. So these conditions must be met or to get the critical point. Now, so these are some stopping criteria. So stopping criteria has been devised on the basis of primal residual and dual residual value. So it is RK norm is less than E primal, and SK norm, Euclidean norm, should be less than epsilon dual. So you need to set them, and R feasibility tolerance for the primal and dual feasibility conditions 5 and 6 respectively. Dual feasibility conditions 5 and 6 are this. 6 includes 6A and 6B. Now, so with all this, we can write our program and the code and to run. So I have taken for implementation, I have taken one example here, the linear and quadratic programming. So I have taken one example like this. So in which I have generated my P and Q and R with some random instances. So I have used MATLAB. So in MATLAB, there is a rand and syntax through which you can generate random instances. So with random instances, I have generated P, Q, and R. Remember, I have generated this P, which is a positive semi-definite, symmetric, and semi-definite matrix. So with all this, see here P equal to 0, the above problem 8 reduces to standard form of linear programming. Okay, so I have divided this example into two different examples. So one in which P equal to 0, that means it will become a linear programming problem, Q transpose X plus R. So it is just a linear, only linear variables will be there, power will be 1. So it will be a linear programming problem. So here is the example. When p equal to 0, we have this problem. So this is one problem. And its ADMM will be written like this, where f of x is q transpose x, and domain of f is taken from ax from such x for which ax equal to b is the objective function, and g is the indicator function of the non-negative orthant. So you see, this is one example of one linear problem. And now this is one example of the quadratic problem, but p is not 0, but I have taken some r 0. So I have taken f of x. So this is another example, second example, two as my numerical problem. So this is the second example in which f of x is half into x transpose px. Now p is the semi-definite matrix. Remember, I have generated from random instances, so which I have not shown here for p, and q also have been generated from the random instances. Or we can also have r. Also, the r also can be generated with the random instances. It's not a problem. Now, you see, we have two problems. One is problem 9, and the other one is problem 11. Now, problem 9 is ADMM form is 10. So I'll call it a problem 10 I need to solve, and the problem 12 I need to solve. So problem 10 and 12 I need to solve. So this is how ADMM iterations for problem 10 and problem 12. So these are the iterations which I have written. So these are my steps. So f of x, you know. So f of x can, for one problem, it will be linear, q transpose x, and the other problem, it will be x transpose px plus q transpose x. Maybe if you need r also, you can include. So this is how my steps are, ADMM steps. So x object is a equality constant least square problem, and b plus means here x k plus 1 plus uk plus 1 over plus. That means the vector obtained by taking the non-negative part of each component of b. And the last one is the dual object here. So this is what the result I got by processing it in my using MATLAB software. So I have written the program, and now while generating p, the number of variables I have given is 500. The number of constant which I have given for this problem is 400. So number of constraints, this is related with a, the number of constraints. So this is related to n, because ax equal to b, the constraints. So now with this we have solved. In two methods. One is ADMM and one is CVEX. CVEX is a very well popular method in which we solve semi-definite programming. So CVEX for quite some time have been treated as, not quite some time now, also in so many cases, CVEX is a very strong method. So we have taken CVEX, which is a state-of-the-art method. Actually, CVEX is given by SGPT3. So CVEX solves the semi-definite programming problems. That means our problem, if can be transferred to or equivalent semi-definite program problem, then it will solve. So that is what I have done. I have also converted that problem to semi-definite programming problem, and then used CVEX to solve. Now you see the objective values which has been obtained after 69 iterations in ADMM is 370.96, and the objective value which has been obtained by CVEX is after 15 iteration is 371. So the time the ADMM takes is 4.6, whereas the CVEX takes is this. And these are the residual values which must goes to 0. So this is the R norm and this is the S norm, which are very close to 0, and these are for CVEX, relative primal feasibility, infeasible values, and this is for relative dual infeasible values. Now you can see that the ADMM doesn't perform better than CVEX because ADMM took much time then, even though the solution looks better, but not that it is 371 and that is 370.96. So it took more time than this. So then what I have done, I have increased the number of variables, and okay, this graph is the residual convergence, means how the residue is converging. You see here, this is the epsilon value. So epsilon you can see we have set it here, E epsilon priori, and this is for S. So these are the values are in the dotted line. So whenever they were crossing, the iterations were stopping there. So it is here. So iterations were stopping at 31 iterations, and here. Okay, sorry. It is crossing here 31, but here it is crossing in 69. The dual residual. The primal residual at 30 around and 69. So that is why the program stops at 69. Now, what I have done, I have increased the number of variables. Now, this is the number of variables I have increased. It is 1500 now, and constants remain same. Now you see, okay. So then it became a new problem. Remember, it is not the old problem. Since I increased the number of variables, so it is a new problem whose objective value has been coming like this. So it is ADMM found it 829 point something, and the CVEX found it 828.94. Again, the time difference you see and the number of iterations of ADMM is not impressive. It is quite large. And the residuals you can see. So as I have said, so they came accordingly. So the linear programming, we are finding that it is not that impressive. So ADMM, why should I take ADMM? No. I have not seen there are so many other things like now I will shift to quadratic programming mode. Now you see the quadratic programming. So here means I am solving X transpose AX plus Q transpose X plus R or C, whatever. This problem. So this is a quadratic problem. Before I was solving Q transpose X plus C. So now with this, I have used 100 variables, and you see the objective values were close, but you see the CPU time. It is much lesser than this, and the number of iterations were little higher. And you see the how the convergences, how it is converging. So now the ADMM is impressive. When the problem become complex, quadratic programming is much complex problem than the linear programming. Now you see I have increased the number of variables to 500. So with the 500 variables, what happens? You see, remember when I have increased the variables to 500, it becomes another problem. It is not the same problem which we have seen in 100 variables. Number of constraints I have not given. It is an unconstrained problem which I have solved. So now what happens? You see the objective values have been produced are almost same, but the CPU time you see, the ADMM produced it with 0.026 seconds, whereas CVEX took 7.19 seconds. The number of iterations were also less in ADMM, and in CVEX it is quite high. And you see the residual convergences, the primal residual and dual residual, see here. So this actually tells me that the ADMM is quite impressive when the number of variables and the degree of the variable goes. That means when it is a higher order problems and the number of variables are also more, then ADMM performs better than this CVEX. So here is some conclusion on the basis of these experiments. So the conclusions are ADMM is faster for large scale and complex problems. Still, because we have divided this ADMM to sub-problems, so ADMM is actually converging much faster because it is divided into sub-problems. Inclusion of restart conditions and acceleration steps can make the ADMM converge more faster. So this is something for the further study. So you can include restart conditions or acceleration steps to accelerate the iteration process. And there is another thing, you can also distribute the task by parallelizing it so that the results you can obtain faster. So these are some conclusion about the ADMM, and this is how this first order method ADMM is quite impressive. And this is how you can solve. So this is one of the method which you can solve, which is a first order method by which you can solve a large scale problem. And ADMM can solve so many complicated problems in computer vision, in machine learning, and in image processing. And it is doing wonders in them, in all these areas. So there are so many other areas as well. Okay. So with this, I hope you have realized the power of optimization, moreover the first order methods uh, in these fields, the machine learning, computer vision, image processing. So these are some references I have used. So this is the material by Stephen Boyd, who is very famous. This material is a nice material on ADMM. And this is, if you want to know semi-definite programming about CVEX, you can use this material by Hallenberg.